This portion of Sesame Street is being brought to you by... Tomorrow? 727 then? We're back here to discuss the front panel of the 727, and we'll start off with the overhead panel. In the upper left-hand corner of the overhead panel are your hydraulic power control switches. The first one we're going to look at is labeled aileron. You have a switch for System A ailerons and the System B ailerons. Now, what we have on the airplane are not really two separate ailerons for System A and System B, but rather a set of ailerons that are jointly controlled by both System A and System B. And either system will do it alone. The aileron power pack is located in the left wheel well and has inputs from both System A and System B. One system only operating the power pack, of course, would be at a slower rate. We have two sets of ailerons on each wing. We have an inboard set and an outboard set. There's a picture of the wing of the aircraft. The outboard set is not continuously operating. The outboard set will be locked up when the flaps are fully retracted, and then as the flaps are extended to a greater degree, it will come into play more and more. So until when you're at your final approach flap setting, you'll get full use of the outboard ailerons. The inboard ailerons are operated, as I said, by the aileron power package that's in the left wheel well, and they're used all the time. On each aileron is a tab. They are not trim tabs, by the way. The trim mechanism is performed by merely recentering the power package that's in the left wheel well. So if you lose hydraulic power, you don't have aileron trim. What these tabs do are reduce the workload for the ailerons. When we have a powered operation, these tabs are merely balance tabs. They move opposite to the direction of the airfoil. So when this aileron goes down, the tab goes up. When this aileron goes down, the tab goes up. What about when we lose both System A and System B hydraulics? Then this tab becomes a control tab. If we want the aileron to go down, we manually control the tab, we manually make the tab go up, and that in turn flies the aileron down. So that's a control tab. How about this tab here? Well, that's just a balance tab. In loss of hydraulic situation, this tab just is along for the ride. If the outboard aileron is unlocked by the flaps being extended, then we have a follow-up mechanism to connect the inboard and outboard ailerons so that when this powered, mechanically powered control tab moves up, for example, it would fly this aileron down. This aileron is connected to this aileron, so this aileron would fly down. And this tab, since it's always hooked up as a balance tab, would move up. Now, if you don't believe that, what I suggest you do is go out to the airplane when it's sitting on the ramp with no hydraulic power to it and move the airplane yoke to the right or to the left. And what you'll notice is, you'll notice this little tab on the inboard aileron move and nothing else moves. So that's how you could prove it to yourself. Now these two switches will, if uncapped and turned off, they will turn off either System A or System B power to that respective set of portion of the aileron control pack. Right below it we have an elevator System A and System B set of switches. And they do the same thing for the elevator. The elevator, we have one elevator on each side of the vertical stabilizer. Both of those two elevators then are controlled jointly by System A and System B. And again, either one of these hydraulic systems will power the entire elevator. However, if we lose both System A and System B, we will get mechanical operation of the elevator, although we'll only have about 50% of full elevator travel. Of course, as you know, we use the stabilizer and reposition the entire stabilizer to trim the airplane. And the elevator is just at the back end of the stabilizer. And the way we fly the 727, normally we would like the elevator to be more or less spared with a stabilizer. So whether or not you've lost your elevator, you still have stabilizer authority if you have stabilizer trim. And we've got two trim systems for the stabilizer, both electric motors with manual backup. We've got a high-speed motor, which is activated by using the trim control on the yoke, either pilot's yoke. And we've got a low-speed motor, which is called the cruise trim, and that's activated by the switch on the center lower pedestal, or by engaging the autopilot. The autopilot uses the low-speed cruise trim also. So we've got, and plus we've got a manual way of, through a series of cables and a linkage, turning the jack screw manually, and that in turn repositions the stabilizer. So we've got one jack screw, two electric motors, one high speed, one low speed, and a manual backup for the stabilizer. The rudder system has two switches, and I discussed one of these a little bit before. We have a System A rudder switch, which is ganged to a standby rudder switch, and we've got a System B rudder switch. And again, the purpose of these is so that we have both System A and System B hydraulics going to the rudder power system. And either one of these will fully power the rudder, although if it was only one system, it would be at a slower rate. There's no manual backup for the rudder, and that is why we have a standby rudder switch. If we ended up losing both System A and System B, we could still power the lower rudder by use of the standby rudder switch. What we've got as you know, the upper rudder is powered by System B, the lower rudder is powered by System A. We've got a separate actuator for each of those. Those are actuators. In addition, the standby rudder is another actuator which powers the lower rudder. So if we end up losing both System A and System B, we could, by turning off the System A rudder switch, which is ganged to the on position of the standby rudder switch, get that standby actuator into operation, and it in turn would power the lower rudder. Would we have a yaw damper attached to that? No, we wouldn't. We're going to talk about the yaw damper in a little while, but I want you to bear in mind that when we do that, we've lost our yaw damper. Now the spoiler switch here, the spoiler switch arrangement is a little different from the other switches. You'll notice on your panel foldouts that you have, and if you can read this writing here, the aileron switches are called System A to the left, System B to the right. Elevator, System A to the left, System B to the right. Rudder, the same thing. The System A switch, ganged to the standby rudder switch, is on the left side, System B switch on the right. How about our spoilers? No, the System B switch is on the left and the System A switch is on the right. Don't ask me why they did that. Now these, the spoiler switch here controls your flight spoilers. Only the flight spoilers. Does not control your ground spoilers, and that's an important thing to remember. I'm showing you the arrangement of spoilers on the wing now. We've got four spoilers outboard and 3 inboard. The 2 outboardmost of your flight spoilers are powered by System A. The 2 inboardmost are powered by System B. And then of the other spoilers, we've got B on the outboard and then 2 A's. Each of these has its own actuator. The two inboardmost spoilers shown here, powered by System A, are called ground spoilers, and they are not in use in flight. So our flight spoilers are these 5 outboardmost spoilers that you see here. And these other two are called ground spoilers, and they have only 2 positions. They're only capable of being placed in 2 positions, either full up or full down. And of course the airplane has to be on the ground, and you extend the speed brake switch, and then these things come all the way out. In the air, they will never come out. All the rest of these, which we call flight spoilers, as you know, are capable of varying increments of extension, from fully flush to fully extended. By the way, all it takes is about 7 degrees of yoke movement before you start getting some mix of spoilers in with the ailerons. So if you have trimmed the ailerons to the point where your yoke is more than 7 degrees off center, you're probably going to be getting some spoilers also. And in that case, you would probably have trim drag due to those spoilers hanging out there. It would be beneficial to discuss just for a second also the position of these spoilers on the top surface of the wing. They are positioned actually further back than we have it drawn here. I have it drawn up toward the leading edge just so we have room to talk about them. But in reality, they're fairly well toward the aft end of the wing. And what occurs as you extend flaps, as you know, the center of pressure moves aft on the wing. And one of the major reasons for only using flaps 15 for any kind of hydraulic system problem is that if you've lost, say, your A or your B system, then these spoilers would be unpowered and they would be subject to spoiler float if you had a lot of low pressure along the top of the wing right over where those spoilers happen to be. And so we use flaps 15 for hydraulic, for example, for a complete hydraulic failure, so that we're at a high enough angle of attack so that the center of pressure does not move back, move aft on the wing over these spoilers and suck up some of these spoilers, which we call spoiler float. They don't float symmetrically. So we could end up getting all the spoilers floating on one wing and not on the other, and come down final with the yoke at a 45-degree angle or something, and that's not a real good deal. By the way, at breakfast this morning, the waiter just told me the difference between 727 pilots and canoes. Canoes tip. Next to these hydraulic power switches, we have a stall warning system, a set of either 1 or 2 switches, and it might also have a disc here, a black and white disc. Now that'll depend upon which model of the airplane you get. The early short models, the late short models, or the long-bodied airplanes. In any case, the stall warning procedure consists of either pressing the little button or moving the toggle switch to the test position. And when we do that, during our panel setup before the flight, the amber power off light will go off. The stick shaker will shake. And if we have one of these discs, it'll rotate. What does that all mean? Well, if the light goes out, it means that we have both power to the stall warning computer and heat to the stall warning vane. So we're testing computer power and stall warning vane heat when we go to test and the light goes out. And of course, if the light doesn't go out, it means one of those things ain't there. Either we do not have heat to the vane or we do not have power to the computer. If this disc rotates, it means we've got good wiring continuity between the transmitter and the flaps and the stall warning computer. Because let's face it, without this disc, what if the wire between the flap transmitter and the stall warning computer was broken? We could do a perfectly valid test and we'd never know that, because the only thing we'd know is that the vane is being heated and the computer is being powered. So now we have a wiring continuity check. So that's a good deal. What if you're flying along and that amber light comes on? What's it mean? Well, it means the same thing it means when you're doing your panel setup. It means you either lost heat to the stall warning vane or you lost power to the computer. Now what I would do is I'd test the system. You test it and you get a stick shaker, and it's not going to shake the airplane or anything. And if the stick shaker shakes, it means what? It means that the stall warning computer works, because the computer is the thing that talks to the stick shaker. If the stick shaker doesn't shake, it means the computer doesn't work. It could also mean the heater doesn't work. We don't know, but for sure the computer doesn't work. We're talking about the stall warning computer. So that's the stall warning system. Right below that, we've got an altitude alert horn. And you're all familiar with the melodious sound of that. And what it does is, of course, it alerts you as you're approaching or passing through an altitude that's set on the altitude alert panel on the lower front portion of the instrument panel. When does it sound? Well, it sounds 900 feet prior to getting to the altitude as you're approaching an altitude, and it sounds 300 feet past the altitude if you went to sleep at the wheel and overshot your altitude. Below that, we've got the ground proximity warning system, the GPWS. We've got a guarded switch with a safety wire, which if you can inhibit the entire GPWS by uncapping that switch, or you can just leave it capped and put up with all the warnings you're going to get from it. Let's take a look at the different warning systems that the GPWS provides. Let's say that we're making an approach and we have the GPWS in the normal or armed position. It's going to give us several different warnings based on how high above the terrain we are. The first warning will occur at 2,450 feet above the terrain. That's 2,450 feet radio altimeter. And that would be for an excessive rate of descent. When I say rate, I mean in terms of feet per second down. The number is unimportant. So at 2,450 feet, when we have a barometric rate of descent as sensed by the air data computer, the GPWS will give a pull-up signal. The next warning would occur at 1,800 feet above the ground again, and that would be for excessive closure with the terrain. So that would be an excessive rate of decrease of the radio altimeter. Below 1,800 feet, we would get a pull-up signal again. Coming on down, when we reach 500 feet, when we are below 500 feet, without being in the landing configuration, which is landing gear down and flaps either 30 or 40, we will get, again, a pull-up signal. The GPWS is only active, it is only actively giving you warnings between 2,400 feet and 50 feet. The other pull-up warning we would get is on, for example, a takeoff or missed approach if we descend prior to reaching 700 feet, again, above ground level. Those are the pull-up warnings we get. There's one other GPWS warning function that we'll discuss separately now, and that is the glide slope warning function. The glide slope warning function, as you know, gives you the glide slope aural warning if you are below 1,000 feet above the ground with the landing gear extended, with number 1 VOR, with the number 1 VHF navigation receiver tuned to an ILS frequency, and you get more than 1 1/3 dots below glide slope. And that also is inhibited below 50 feet. So now we know everything that gives you the warning for ground proximity warning systems. Let's see if we can figure out what are the inputs to the entire system. Well, up here at 2,450 feet, when the system becomes active, we're looking for an excessive rate of barometric descent as sensed by the air data computer. So we could say that the first input then is the air data computer. And how does it know to look at excessive rate of descent? Well, it also gets an input, as we already discussed, from the radio altimeter. At 2,450 feet is when it starts giving us active warning. So radio altimeter is another input. Radio altimeter obviously is an input here at 1,800 feet and again at 500 feet. And the other inputs at 500 feet are the landing gear and the flaps at 30 or 40. That is to say, flaps in the landing configuration. And then finally, the other input we have, and it's obviously for the glide slope function, is the number 1 nav receiver. Okay? Knowing all the thresholds here, I assume that we could, by thinking about it a little, figure out all the inputs if somebody ever asked you. The next switch below the ground proximity warning system on our panel, on this panel, is the auxiliary vertical gyro switch. Now, not all aircraft have an aux vertical gyro. Those that do have gotten themselves an extra gyro for the attitude indicator, which is standing by, it's pulling reserve until it's called on with this switch. And by placing captain on aux, we can let this other vertical gyro provide signals for the captain's attitude indicator. And by going first officer on aux, we can allow the first officer's attitude indicator to get its signals from our standby or auxiliary vertical gyro. In the normal position, it's merely being powered by standby AC power, and it's ready to go in when you put it in with this switch. It's not connected to anything, in other words. It's just fully spun up and ready to go to work. If we had an attitude indicator power failure, let's say we lost standby AC power. Now, standby AC power, as you know, powers the captain's attitude indicator. Would the aux vertical gyro work for us? The answer is no, because when we switch it over to either captain or first officer, it assumes the power source of the gyro that it replaced. So if the gyro goes bad because it is unpowered, then the aux vertical gyro will not do us any good either. In other words, when we place the aux vertical gyro to the captain on aux position, the aux vertical gyro is then getting its power from standby AC. And by the way, standby AC is what powers it in the normal position. When we place it over to first officer on aux, it is now getting its power from the same source that powered the previous first officer's vertical gyro, which is the number 2 AC bus. So, the aux vertical gyro, the important thing to remember is that it will not substitute for a power loss. It will substitute for a mechanical failure of the gyro, though, if the captain's gyro failed or the first officer's gyro failed. And that's the vertical gyro. Right next to that, we have a switch that says emergency exit lights and an amber light here that's labeled unarmed. A 3-position toggle switch off, armed, and on. Now, the purpose of this is to allow the emergency exit lights to come on when you have an interruption of essential power. And in the armed position, that's what will happen. If we lose essential power or battery bus power, the emergency exit lights will come on. In the on position, if we take this toggle switch and place it to on, the emergency exit lights will come on. What's powering the emergency exit lights when they either come on automatically or when we place them on? Well, as you know, they are self-contained batteries are powering them. So if you have a new set of emergency exit lights, the batteries will probably work for 10 minutes or so. If they're old and the batteries aren't too great, maybe they won't work that long. Maybe they won't provide adequate illumination for that long. And when we place the switch to off, it means they are not going to come on, period. And of course, we would place this switch off when we shut down the airplane. Otherwise, as soon as we take off all our power sources from the airplane, essential power and then battery bus power, the emergency exit lights would come on if we had forgotten to turn this off. The unarmed light means what it says. They are not armed. So if we place the switch to off, will we get an unarmed light? Yes, they are no longer armed. If we place the switch to on, will we get an unarmed light? Yes, they are no longer armed. They're on. So the light means exactly what it says. Right above it we have a windshield wiper switch with 5 positions: park, off, low, half, and 3/4, and high. That's 6. 6 positions. We have 2 separate windshield wiper motors, each powered by a different power source, one for the first officer, one for the captain. Right above that we have rain repellent switches, one for the left windshield and one for the right windshield. Now the rain repellent, as you know, is a surfactant that we squirt onto the windshield, and it causes the rain to adhere, the water surface to adhere in a thin film to the windshield, and we can see through it clearer, kind of like looking through an aquarium. The rain repellent itself could either come in the 1-bottle system or the 2-bottle system. If you have the 1-bottle system, you'll have a visible float in the container, in the rain removal reservoir, and you can check the fluid level of the rain repellent fluid. If you have a 2-bottle system, you just have a selector so that you use 1 bottle until it goes dry, and then you switch over to the other bottle. And then after you land, you tell maintenance that 1 bottle's dry, and they'll give you a new bottle. So you always have at least 1 and probably 1.5 to 2 bottles of rain repellent fluid. Rain repellent, as you know, should only be used in very heavy precipitation. It's used in conjunction with the windshield wipers, and you never use it on a dry windshield because it is kind of corrosive, and it'll ruin the, first of all, it'll obstruct your vision, and second, it'll ruin any aircraft painted surfaces that it comes in contact with under dry conditions. Over here we have the starter switches, the engine ignition and starter switches. Now on some airplanes the arrangement of switches, on some airlines airplanes the arrangement of switches is slightly different, but I think our discussion will cover all the different conditions that we need to discuss. The start valve arming switch arms the starter valve so that when we go to the ground position on any of these start switches, the starter valve will open. And if we don't arm the starter valve arming switch, then going to ground will not accomplish anything. Going to flight will give us continuous ignition. So going to ground does 2 things. It gives us ignition, and it opens the starter valve, assuming the start valve arming switch is armed. Going to flight does 1 thing. It gives us continuous ignition, either high energy or low energy, depending on which we select with our start lever. The start lever controls whether we get high or low energy ignition. And the way it works, here's a picture of our throttle quadrant, and of course we have the start lever on the throttle quadrant. At the very bottom we've got the first notch, which represents starting ignition, which is high energy ignition that is 28-volt DC power. And then the idle position, the position we leave it in during flight, is low energy ignition, which is 115-volt AC power. Well, many airlines have a procedure that if the starting ignition does not work, we can go ahead and start the engines and dispatch with only the low energy ignition available. And the way we do that is we merely, when starting the engine, place the start lever at idle rather than start. And there are some other procedures associated with that. Could we do that if we were making a battery start? No, as you could see, we couldn't do that because a battery start means we don't have any AC power. The battery power provides DC, but if our starting ignition doesn't work, we don't have any available there. Low energy or idle ignition is AC, and since we're making a battery start, we don't have any AC. So it's important to remember that if you are going to use the low energy ignition starting procedure, you have to have AC power to do it. In other words, A battery start can only use the start position, the high energy position of your starting valve, of your start lever. The next set of switches we're going to discuss are on the alternate flap control panel. Now there are 3 switches here. One is a safetied and guarded switch called the alternate flap master switch, normally safetied to the off position. And then we have 2 toggle switches, one for inboard and one for outboard flaps. Spring-loaded to the center. Well, that's not correct. They are positioned to the center. They are spring-loaded to the center from the down position, and they will remain in the up position if you toggle them in that direction. Several things happen when we uncap and move this toggle switch that is the alternate flap master switch. First, let's look, though, at the arrangement of the flaps on the airplane. We have an inboard set of flaps and an outboard set of flaps. The way the flaps are connected is there is one torque tube which drives 2 jack screws for each set of flaps. One jack screw for the left inboard, one for the right inboard. A different torque tube arrangement and jack screw for the left outboard and for the right outboard. The torque tubes are turned by hydraulic motors. Which hydraulic system runs your flaps? Of course, your A system. So we've got a hydraulic motor for each flap, inboard and outboard, torque tube assembly. Piggyback on that same torque tube, mounted right alongside it, is an electric motor. Now their position in the wheel well is of no importance to our discussion here because it's not like I have it drawn here. So when we move the flaps hydraulically, as is our normal case, we are moving 2 hydraulic motors turning torque tubes which drive jack screws and extend our inboard and outboard flaps. When we uncap and move the alternate flap master switch to the on position, what we are doing is turning off all hydraulic pressure to those motors. So we have lost hydraulic control of our trailing edge flaps. So that's one thing. We've also lost all hydraulic pressure to our leading edge devices. And as you know, we have leading edge flaps and leading edge slats. Now the leading edge slats will lock up mechanically if we lost hydraulic fluid. The leading edge flaps will tend to droop. But they are held up hydraulically normally the entire flight. And what we are doing now is we are cutting off all hydraulic fluid to them. Why is that important? Well, what if we had a leak in one of those actuators? After all, I told you that they're being pressurized the entire flight. If we had a leak in one of those leading edge actuators, this would be the way to stop it. So we cut off hydraulic pressure from the trailing edge flap motors. We cut off hydraulic pressure from the leading edge devices. We arm the alternate flap electrical up and down, inboard and outboard switches. And those switches for both the outboards and the inboards are what control our electrical flap operation. We're using electrical motors, very high draw on current. If we're down to the point where we only got 1 or 2 generators operating, we're going to have to be careful how we use these things. Electric motors that drive the same torque tubes at a lot slower rate to extend our outboard or inboard flaps. Now, as I mentioned before, if we go to the down position, the extend position, they're spring-loaded back to the off position. If we go to up, they remain in up. And why would you imagine that would be? Sure, so that we have go-around capability, so that we don't have to hold our hand there if we need to raise the flaps electrically. The other thing that happens when we turn on the alternate flap master switch is we start the standby pump. And remember, we discussed that in our discussion of hydraulics. We pressurize the standby hydraulic system. We start the standby pump so that we have the lower rudder powered, and that we can get extension but not retraction through the standby system of the leading edge devices. So the four things that happen when we uncap and move this switch one more time: we cut off all hydraulic pressure to the trailing edge flaps. We cut off hydraulic pressure to the leading edge devices, flaps and slats. We arm the electrical control switches, and we turn on the standby pump. The flight recorder, shown directly below that, has an on-off switch and an amber light that says off. That amber light will illuminate for several reasons. If we lose power to our flight recorder, it'll illuminate. If we don't have the tape, the flight recorder tape moving through the flight recorder, it will illuminate. So if we had a break in the tape, if we had a lot of slack in the tape that was not yet taken up, if we had a tape drive problem, or if we had a power interruption or a power failure of our flight recorder, that light would come on. Placing the switch to on should start the tape moving through the flight recorder. As you know, the regulations say you have to have that thing on from the beginning of the takeoff roll, but if you forgot to turn it on, what would happen? Well, it's hooked into a micro switch so that as soon as the airplane is in the air, it'll turn itself on even if you forgot. So it's second officer proof. The next set of switches we have, of course, are the no smoking and the fasten seatbelt switches, cabin attendant call button, very important button, especially when coffee's getting low up in the cockpit. Okay, and the next thing we're going to discuss is the CVR, the cockpit voice recorder. That's, as you know, that is Big Brother watching us, and there are two buttons on that thing. One says test and one says erase. Now, to test the system, what you do is you press the button and you notice two flicks into the white band of our monitor meter. And you should plug in your headset to our little phone jack here. Only the second officer's headset fits on most airlines because they're different size jacks. You plug in your headset and then you talk into the microphone, and a couple seconds later you should hear your voice coming back to you. That's the way to test it. Everybody knows that. Of more importance to us is how do you erase the thing? Well, there are a couple conditions that need to be met. The airplane has to be on the ground as sensed through the strut switch. You have to have the parking brake set, and you have to push and hold the erase button for 7 seconds. Okay, now that's not guaranteed proof that you're going to fully erase it, because as you know, there are a lot of people in government today that through their Watergate experience have had good luck reconstructing erased tapes. However, if you made a gear-up landing, you couldn't erase it, could you? Not unless you just luckily mashed that strut switch at the same time you made your gear-up landing, because, like we said, you need to have on-the-ground sensing, as well as parking brake set, as well as pushing and holding the erase button for 7 seconds. And, of course, our next panel is merely the passenger address control panel. We have a blue light that says the PA is on. Now, it depends on what model airplane we have. On advanced airplanes, the blue light comes on whenever the cabin or cockpit is using the passenger address system. On short-bodied airplanes, the blue light comes on only when the cockpit is using the passenger address system. We've got a little meter here that tells you the volume level, so if you see the meter flicking, it means that somebody in the back is probably talking on the PA system. And then you've got a speaker monitor switch so that you can listen to whatever is being said on the public address system. Anytime you use the PA system from the cockpit, it overrides the PA system in the back. And now in the upper right-hand corner, we have the window heat control panel. Now, there are two types of window heat control panel on the 727. There's the old type, and yes, you guessed it, the new type. This is a picture of the new type. We've got a green and an amber light for each of our number 1 and number 2 windows, the left side and the right side. We've got the off or reset position switch for each of those window sets. And we've got an overheat test and a power on test switch. Turning on either the number 2 or the number 1 switch for either side will turn on the respective set of eyebrow windows for that same side. The green light means that power is going into the window. You've got current draw into the window. What if the window is warm already and you don't need to have the window heated by current? Will the green light come on? No, not necessarily. The green light means that power is going into the window, and if the window, if the airplane's been sitting so that that window is in the sun and it's heated up on a warm day, it's very possible that you won't get a green light come on. If the window overheats, its protective circuitry will stop all power from going to that window, and you'll get an amber overheat light. The way to get that light off is to go to the off/reset position and then turn the window heat back on again. Well, I said, what if we had an airplane that was sitting in the sun and the windows were warm, so when we turn the window heat on, we don't get a green light showing power going to the window? It could be the window's not hot and the thing is just broken. How do we tell? What we could do is we could go to power on test, and that forces current to go to the windows, whether it needs it or not. So we'll get a green light if current really is going to the window. What's the bad deal about that? Well, the bad deal is, obviously, if we hold it to power on test and we're putting current into the window, even if it doesn't need heat, we very well could overheat and crack the window. So you only want to go to power on test to hold it there long enough to make sure that the window really is drawing power, and then you can go back to the neutral position on this switch. If you wanted to test the overheat protective trip-off circuitry, you just turn on the switches, wait for your green lights, and then go to overheat test, and the green lights should go out and the amber lights should all come on. And that means your protective circuitry worked okay. Now we'll discuss the other system of window heat. Speaking of discuss, it reminds me of the story of the guy that goes into the bar and is sitting there on the bar is a little machine with a coin slot, and the bartender told him it's a discussion machine so that you can have a discussion with the machine instead of taking up the bartender's time. Well, this man's sitting there, a gentleman in a suit walks up, puts a quarter in the machine. The machine says, "Hello, what's your IQ?" And the guy says, 180. And the machine proceeds to discuss nuclear physics and philosophy and all kinds of esoteric discussions with the man, and 15 minutes later the machine clicks off. Another man walks up, puts a quarter in the machine. The machine says, "What's your IQ?" The man says, 100. The machine proceeds to discuss baseball scores and CB radios and shotgun racks for pickup trucks and things like that. And after 15 minutes, it clicks off. So this guy goes up there, he puts a quarter in. The machine says, "What's your IQ?" He says, 47. The machine says, "Oh, who's your co-pilot this month?" Okay, so now we're going to discuss the old type of window heat control. As you know, there are two switches, one for the left side and one for the right side. Now, this is a picture of all the different windshields we've got on the airplane. They are labeled L for left and R for right. The number 1 windshield is the one right in front of you, and the number 2 is the co-pilot sliding window, or rather the sliding window. The number 3 is the window behind that. Now, that's an unheated window. Unheated window. Number 4 and 5 are your eyebrow windows. You can turn your switch on to either low or high, and that will not affect how hot the window gets. It just affects the rate of current going into the window. Positioning the, let's say, left switch to low will heat the number 1, the number 4, and the number 5 windows, and it'll heat the number R2. In other words, it'll heat the captain's forward and eyebrow windows and the co-pilot's sliding window. That's called the window heat crossover. Similarly, turning on the R switch, the right switch, will heat the co-pilot's forward window and eyebrows and the captain's sliding window. So that's kind of interesting. After all, what would you do if you had a window arcing? You had a co-pilot's sliding window arcing, and the book procedure is to turn off the affected window heat switch. Which one would you turn off if you had an electrical arcing on the number 2 sliding window on the right side? That's correct. You would turn off the L switch because we have a crossover, and to remove electrical power from the right sliding window, we would need to turn off the left window heat switch. Not something you think about too often. Now we're going to discuss one of the more complicated sub-panels on the overhead instrument panel. And that is the anti-ice control. And I like to think of this small panel here and the next panel down as being one large panel. We've got a duct temperature gauge, an anti-ice duct overheat light, a duct temperature selector switch for engines 1, 2, or 3. Then we've got 5 green lights that tell us about valve positions. So now let's talk about the engine anti-icing system. Then we'll talk about the wing anti-icing system, and we'll see how both of those relate to that control panel we were just looking at. Let's talk about engine 1 or 3 first, shown on the bottom here, okay? We are anti-icing 2 parts of this engine. We are anti-icing the cowl, and we're anti-icing the inlet guide vanes and nose dome. To anti-ice the cowl, we have higher stage bleed air and 1 valve that controls anti-icing air to the cowl, as opposed to the inlet guide vanes, which have a common duct around the entire inlet guide vanes and can get their anti-icing air from both the right engine valve and the left engine valve. And in fact, if one of these valves malfunctioned and did not open when we wanted to open the anti-ice valve for the inlet guide vanes, the other valve, by opening, would provide all the anti-icing we really need. So we've got some built-in redundancy there. Well, the number 2 engine looks just like that, except for one thing. The number 2 engine has a bigger cowl. So we have 2 cowl valves. We've got one set up that looks just like our number 3 or number 1 engine, and then we've got an additional valve to anti-ice the big, long inlet cowl. So you can see now, and this is kind of a complicated diagram here, but we've got the left valve for the inlet guide vanes, the right valve for the inlet guide vane. We've got the normal cowl valve, just like we did on engines 1 or 3, and in addition, an additional cowl valve. Okay? So we've got 2 cowl valves as well as your 2 inlet guide vane valves for the number 2 engine. Okay, now let's talk about the wing anti-icing system. The wing anti-icing system gets its air from engines number 1 and engine number 3. When we open the wing anti-icing valve switch, when we turn the switch to the open position, say for engine number 1, we are actually opening 2 valves. One for your high stage bleed air from engine number 1, and then one for all of your bleed air from engine number 1. Both those valves must open to get a green agreement light on the panel we're going to look at in a second. And this valve must open to get any bleed air into your wing anti-icing system. Now you'll notice that the output of engine number 1 and the air output from engine number 3 comes together and goes up a common duct and then branches out and goes to both wings. You cannot get asymmetric wing anti-icing, ice building up on one wing and not on the other. Can't be done in this airplane intentionally. So we've got the output, the air coming out of engine 1, air coming out of engine 3, coming up, branching off, going to both wings. Now let's look at our control panel again. We've got some switches and some green lights for our wing and engine anti-ice. Now, the first one we'll discuss is at the very bottom, these 3 toggle switches that say engine inlet anti-ice. We have an open and a closed position, and those open and closed positions correspond to opening and closing all the engine anti-ice valves for number 1 engine, all the valves for engine number 2, or all the valves for engine number 3. And as we already saw, we've got 3 valves on engine number 1, and 3 valves on engine number 3, and 4 valves on engine number 2. Those valves are controlled by the switches that say open and close. Now we also have green lights here for engine number 1, number 2, and number 3, and then a wafer switch that says valve position left, cowl right, and wing. If we go to the left position, we are sampling the position of the left valve on engine 1, engine 2, and engine 3. And a green light means that the valve agrees with the switch. They are called green agreement lights. If we go to cowl, we are sampling the cowl valve position for engine number 3, number 1, and the 2 cowl valves positions for engine number 2. And again, green lights mean that the valve agrees with the switch position. And the same for R, or right position. We are sampling the position of the right valve on engines 1, 2, or 3. That's all there is to that. It's kind of confusing because we've got 3 switches and then 3 lights. It would be better, I suppose, but more costly if we had 3 switches and then 3 small lights arranged left, center, and right, 4 small, perhaps jewel-sized lights here, and 3 here. That would be more graphic, but they give us some credit for having intelligence enough to decipher this panel here. Now, when you go to the wing position, you are again looking at wing anti-ice valve agreement lights. And if the 2 green lights here light up, it means that the wing anti-ice valves, remember 2 on each engine, are in agreement with the switch position. The switch can be either placed to close or open or ground test the position it is spring-loaded to. Okay, so if we go to wing and get green lights, it means that the wing anti-ice valves are in the same position that our switch has called for. So far, so good. You can see that this is pretty much a schematic representation. This is the engine, this is the valve, and then the air comes together and goes up to the wings. Well, on our wing and engine anti-icing schematic here, let's first talk about the wing anti-icing overheat indications we get. If we get a wing anti-ice overheat indication while we're in the air, which is the most common time we would get it, it means that the air that is sampled right there is too hot. Air is too hot. Well, how do we know what's causing that air to be too hot? We don't, at this point, know if it's hot air coming from the left side, engine number 1, or from the right side, engine number 3. How do we find out which it is? Well, we take that wafer selector switch that says engine 1, 2, and 3, and we sample the air here coming out of engine number 1, right where the T is. And then we sample the air coming out of engine number 3. Whichever one of those is the hottest is what made this 250 degree, 254 degree switch close and light up your amber wing anti-ice overheat light. Okay? So that means, in flight, wing anti-ice overheat indication means that the air in the common duct is too hot. Okay? If you're on the ground, a wing anti-ice overheat light means that the air out at the wings is too hot. Now that's important because when we're on the ground, we don't have any airflow over the wings, no significant airflow over the wings. So the wings are getting too hot, and without any cooling airflow, they could become damaged. So that is sensed in the left wing root. Now, in addition to lighting up the light, when that switch functions, it closes all 4 of your wing anti-icing valves so that the valves will close. Now, those of you who remember the system are trying to get ahead of me now, and you're saying, wait a minute, you can't open those valves on the ground anyway. And that's true and it's not true. The valves will not go to open just by merely placing the switch to open when you're on the ground. They're protected through the left main gear strut switch. However, you can test these by going to ground test. Remember, spring-loaded switch. Holding the wing anti-ice switch in ground test will open these two valves despite the fact that you are on the ground. That way you can test that your wing anti-icing system works. Well, what would happen if you went to ground test and after a short time you got your green valve agreement lights, you went to ground test to test your wing anti-icing system while you're on the ground with the engines running. While you're holding those spring-loaded switches to the ground test position, the stew comes in and whispers something in your ear, and while you're making arrangements with her, too much hot air goes out to the wings. What prevents that from happening? Right, this protective 93-degree switch, which says when the wings get that hot, these valves are going to close regardless of what you do with the ground test position of the wing anti-icing switches. So that's why that's there. That protects you. Now there's one common occurrence that you will see when making an approach using wing anti-ice. Let's say you're making the approach, your wing anti-ice valves are open, and now you land. Well, as soon as you land, yes, the wing anti-icing valves will close because of the ground safety switch, even if you left the wing anti-icing switches in the open position. What else would you expect to see? Sure, the air in the wings there is still kind of hot. As soon as you hit the ground, the temperature sensor is looking for 93 degrees. It sees it, so instantly that amber light will come on your panel. That would be a common occurrence. It would not be anything to get upset about. So we have seen that the temperature selector on the upper duct temperature panel can go to position number 1 to sample the air here. It can go to position number 3 to sample the air here. In flight, the amber light could come on because of excessive temperature right there in the common duct that goes up to the wings. And on the ground, that amber light coming on due to a wing anti-ice overheat would be because this temperature sensor has felt more than 93 degrees centigrade. Well, there's one other thing that will set off the amber light, and that is an overheat in the number 2 engine. Where in the number 2 engine? Right here, at the cowl of the number 2 engine. And so an overheat sensed here will light up the amber overheat light for the anti-ice overheat panel. And you can determine if that's what the problem is by sampling the air right here. By going to the engine number 2 position, you are measuring the temperature of the air right here. And of course, if that is excessive, you will see that reflected on the temperature gauge. So now that we know how the system works, let's look back at this panel one more time. We've got an anti-ice duct overheat light, an amber light, which could mean, for example, on the ground, that we've got excessive temperature in the number 2 cowl, or it could mean that we've got excessive temperature at the left wing root. In the air, it could mean excessive temperature on the engine number 2 cowl, or it could mean excessive temperature in the common duct that goes up to the wing anti-icing system. How would we tell where the excessive temperature is? Select engine 1, 2, and 3 on our duct temperature selector switch, and look at what the temperature gauge says. If the temperature gauge is high in the number 1 position, then it's probably the wing anti-ice air from number 1 engine is too hot. If it's the number 2, it means that the engine number 2 air going to the engine number 2 cowl is too hot. All right, and the T's here on our schematic represent the temperature gauge. T here for temperature gauge. T here for temperature gauge. T here on the cowl for temperature gauge. The amber light on the number 2 engine is keyed off of the same position that you pick up your temperature gauge at, whereas on the wing anti-icing system, the amber light is tripped off in flight right there at the end in wing, where the 2 air sources come together, or at the left wing root when you're on the ground. Now, how many valves are controlled by these 5 switches? From what we have just discussed, you tell me how many valves are controlled by these 2 wing anti-ice switches and the 3 engine anti-ice switches. Good, very good. 14 valves. We've got 4 valves on engine number 2, 3 valves on engine number 1, 3 valves on engine number 3. So that's a total of 10. Plus 2 valves for the wing anti-ice from engine number 1 and 2 more valves from the wing anti-ice for engine number 3. Very good. Below the anti-icing panel, we have another type of anti-ice, if you will, and that's the pitot heat and the static heaters, if you have static heaters installed, anti-icing control. What we've got are 2 switches, 2 toggle switches labeled on and off, 2 ammeters, one for the left, one for the right, and then a selector switch labeled static pitot, temperature probe box pitot, and elevator pitot. Turning them on turns on all your pitot heaters. You've got 4 pitot heaters on the left, or rather 4 heaters on the left and 4 on the right, unless you do not have static heaters. Some aircraft have just enlarged static ports and they do not have static heaters anymore. Turning the switch on heats up the heaters, and then you can measure the current going to the heaters by taking your wafer switch and looking at the ammeters for each position. The pitot tube for the left side is for the captain's airspeed indicator. For the right side, the co-pilot's airspeed indicator. The temperature probe is for your total air temperature probe. And the aux pitot is the auxiliary pitot that goes to the air data computer. And the elevator pitot on the left and right side are those 2 pitot tubes that we discussed before that go to the elevator field computer on the left and right side. This will complete our discussion of the overhead panel. Now we'll talk about the forward panel. First, why don't we talk about the fire warning switches and controls. We have 2 things to discuss here. One is fire detection and the other is fire protection. First of all, you should be aware that the fire detection is operated by essential AC power. And if you don't have essential AC power, you don't have fire detection. Fire protection is battery bus power. So even if you subsequently lose essential AC, you still have fire protection. Why is that significant? Well, when you're making a battery start, you don't have essential AC. Your indication that an engine's on fire during a battery start is what? That's right, everyone madly running away from the airplane who's out on the ramp. How about during a battery start, do you have fire protection? Yes, you do. You have the capability of selecting the engine and discharging the fire bottle to that engine. When we have an engine fire indication, the appropriate engine light will illuminate, and of course the bell will sound to get your attention to it. As you know, there's a bell cutout button here. The bell will also sound for a wheel well fire indication, which there is no protection for a wheel well fire. It is just the same type of loop that you have around the engines and firewalls, except you don't have anything to discharge into the wheel wells. What happens when you pull a fire handle? Well, quite a few things happen when you pull a fire handle. Basically, though, what you need to remember is pulling a fire handle cuts off the flow of all fluids that pass through the firewall, the engine firewall. It cuts off all bleeds, all air bleeds that pass through the engine firewall. It selects which engine the fire bottle is going to discharge its agent to. It arms the discharge button, and if it's engine 1 or 2, it deactivates that engine's hydraulic pump, low pressure light. We have already deactivated the pump by cutting off the flow of fluids through the firewall. So if you think of it as cutting off all fluids, all bleeds, disarming the hydraulic low pressure light if it's engine 1 or 2, selecting the engine, arming the button, and then the last thing it does is after a 10 to 15 second delay, it trips the field breaker for that respective engine. Now that covers it all. What are the fluids? Well, the fluids are hydraulic fluid if it's engines 1 or 2, all fuel, and where's the fuel cutoff? That's right, at the engine fuel shutoff valve, which is at the aft end of the fuel tank. That's the same valve that you can control with the toggle switch on the second officer's fuel panel. So those are the fluids, hydraulic fluid and fuel. What are the bleeds? Well, it's number 1 or number 2 or number 3 bleed air valves are closed, the air that goes to your air conditioning system, your pneumatic system, because that's bleed air that passes through the firewall. If it's engine number 2, it's anti-icing bleed air that goes to the cowl, because that's bleed air that goes through the firewall. How about the engine anti-icing bleed air that just goes to the inlet guide vanes? No, because that never passes through the engine firewall. Okay? If it's engines number 1 or number 3, it cuts off the bleed air that goes to the wing anti-icing system, because that is bleed air that goes through the engine firewall. So the easiest way, I think, to describe it is all the bleeds, all the fluids that pass through the engine firewall are cut off. Okay, and once again, it disarms the low pressure light for that hydraulic system merely so that you don't have to look at a light the rest of the flight. I think that's a dumb idea, but that's the way the airplane was designed. Okay, and of course we've got a bottle discharge button, which is not even an active button until the handle is pulled, because like we said, pulling the handle arms that button. Okay, we've got a bottle transfer switch, and we can select either the right or the left bottle, and when the bottle is discharged, we get a discharge, a bottle discharge light, and that is a low pressure light. When that light illuminates, it means you don't have any pressure left in the bottle. As you know, those bottles are located in the right aft air stair. Some airplanes say they want you to, some airlines specify left bottle is discharged first. And the only reason for that is so that it's easier to service the left bottle because it's closer to the center of the air stairs. Pneumatic brakes. How do the pneumatic brakes work? Pretty good. To use the pneumatic brakes, we are porting pneumatic stored air onto hydraulic fluid, which in turn is sent to the shuttle valves back at the brakes, and hydraulic fluid is going to the brake. So it's not air going to the brake assembly itself, it's hydraulic fluid going to the brake assembly. You don't have differential braking when you're using pneumatic brakes. You have a limited amount of braking, and how you get that braking is determined by how you move that handle. And normally you move the handle clockwise to the full increased position, wait till the brakes start to catch, and then you modulate the amount of braking you have with the handle. Clockwise is more, counterclockwise is less. The SAI, Standby Attitude Indicator. Most of you are aware of what caused the requirement for a standby attitude indicator, and all except the advanced airplanes have a switch mounted up here. This is not that switch, but it's in this position on other airplanes. An on-off switch for the standby attitude indicator. And the way that thing works is, has its own battery on all except this airplane I'm talking about. It has its own battery. That battery will power this little standby attitude indicator with a self-contained gyro for 30 minutes after you lose airplane battery bus power. So what we really have is a standby attitude reference probably for about an hour if all the generators crapped out on us, don't we? Sure, because if we lost all our generators, we would still have battery bus power to the standby inverter, which will give us standby AC power to power the airplane attitude indicator, right? And then that airplane battery is going to last for about an hour. It's also powering the standby attitude indicator at the same time. When the airplane battery finally poops out, then the standby attitude indicator battery comes into play, and it'll power the standby attitude indicator for another half hour. So really, if we had a total electrical failure, we could count on that thing giving us reliable indications for about an hour. All except on the advanced airplane. The advanced airplane, for some reason unbeknownst to me, has the standby attitude indicator powered by the airplane battery, which means that if you lose the airplane battery, you've lost your standby attitude indicator also. Now, when I say lose the airplane battery, that could be, and I'm talking about the battery bus, not the hot battery bus. It's not hot wired to the battery, it's on the battery bus. If you inadvertently turned the battery switch off and had electrical failure, you've lost your standby attitude indicator also. So I think that is not a giant step forward for mankind when they did it this way, but that's the way it works, okay? On the advanced airplanes only, there is no on-off switch. It's on whenever the battery bus is powered. Let's talk about the engine instruments. You know, we've got 5 instruments for each engine on the forward panel here. Which ones of these are self-powered and which require some sort of outside power? Well, the easiest way to remember it is the ones with the green arcs, that's N1, N2, and EGT. The ones with the green arcs are self-powered. They have their own power source. N1 and N2 have tachometer generators, and of course the EGT has its own power source. The engine pressure ratios, the EPR gauges, require AC. And the fuel flow gauges require both AC and DC. It's an AC gauge and a DC meter movement. So it requires both AC and DC. If you lost AC, the meter would freeze where it is. If you lost DC, the meter would go down to 0. So those are the power requirements. Engine limitations vary by the type of engine you have on the airplane and the airline, because some are airline type limitations. But let's just discuss the 2 different types of engines we have in predominance on the 727 fleet, and that's the JT8D-7 engine and the -15 engine. And as you know, the -15 engine is more powerful. And that's really all we need to discuss about it. We're not going to go into detail on engine limits and on how much thrust the engines put out, because these are just straight numbers that you can get out of your own airline's flight manual. The flap indicators. There are inboard and outboard flap indicators. Now it looks, as you know, it looks like there's one little needle on that gauge, but in fact there are 2. They are coaxial needles, and one represents your right set and one represents your left set. And normally, unless you had some kind of flap asymmetry, you would expect it to look like one needle, because both needles would be pointing the same way. And so your upper gauge is for your outboard flaps, your lower gauge is for your inboard flaps. If you want to move, if you want to use the alternate flap system, these are the 2 indicators you'll be looking at while you're moving the flaps electrically. There's nothing wrong with moving your outboards and then your inboards, or your inboards and then your outboards if you happen to be down to the alternate flap system. That's no problem. Split flaps, which you are correcting with the electric motors, is no big problem. Asymmetric flaps, however, is a big problem. And there are, of course, book procedures, be it irregular or emergency procedures, to cover asymmetric flaps, which would be seeing 2 needles on one gauge. That would mean the left flap, either outboard or inboard, is at a different position than the right flap. Below the flaps, we have an amber and a green light that says LE flaps, leading edge flaps. And basically, what we're looking for, the amber light means that the leading edge flaps are not in the position called for by the trailing edge flaps. The green light means the leading edge devices, flaps and slats, are in the position called for by the trailing edge flaps. So let's see how that works. When we go to flap position 2, on our flap selector handle, then we are programming this light to be looking for leading edge devices number 2, 3, 6, and 7. And it will show amber until we get exactly 2, 3, 6, and 7, and nothing else more or less extended. When we go to flap position 5 or greater on the flap selector handle, then we are programming this light mechanism to go green when we have all of our leading edge devices extended. Nothing more or less, well, nothing less will suffice. So you can see then that when we go to flaps 2, we'll get an amber light until we have what extended? That's right, leading edge devices 2, 3, 6, and 7. And then when we go to flaps 5, the light will go amber again until we get them all extended. Then it'll go green. When we're raising our flaps back to flap position 2, it'll go amber again until 2, 3, 6, and 7 only are extended. Then it'll go green, and then when we raise the flaps completely, it'll go amber until all the leading edge devices are retracted. And then the light will go off, because we don't want a light staring at us the entire flight. Now, throughout our discussion, we've mentioned some things that are that work off of micro switches on the flaps, and let's discuss now what those things are. First, we'll discuss what the items are that are controlled by switches on the different flap segments, and then I'll give you a couple hints at how to remember them, okay? Let's talk about the outboard flaps first. We've got the most things wired through switches on the outboard flaps. The first thing we'll discuss is the tail skid. On short-bodied airplanes, the tail skid works off of a micro switch, which is used in conjunction with the outboard flaps. I might as well put tail skid extension here so you realize that when the flaps, the outboard flaps go to position 15 or more, we get the tail skid coming down when the landing gear is extended. Leading edge devices, they get their programming from the outboard flaps. If the outboard flaps are up and the inboard flaps are extended, you won't get any leading edge devices. For example, a case of split flaps. In that case, you would have to get the leading edge devices out using your alternate flap system. Outboard ailerons, we already discussed that in that the outboard ailerons only come into effect when our flaps are extended. The greater amount the outboard flaps are extended, the more the outboard ailerons are extended until some point prior to getting final flaps, we have full use of the outboard ailerons. The takeoff warning horn, that gets its programming off of the outboard flaps. In other words, the takeoff warning horn, when it is looking for a takeoff flap setting, is only looking at the outboard flap segments. Okay? What is the takeoff warning horn? Well, it's an intermittent horn that sounds whenever the number 3 throttle is positioned toward the takeoff range and you do not have takeoff flaps, trim in the green band, and speed brake stowed, speed brake down, speed brake handle down. Those are the 3 conditions that will sound the takeoff warning horn. If you don't have the speed brake down, if you don't have trim in the green band, or if you don't have takeoff flaps set. The landing gear flap horn. That's a steady horn that sounds if you have the flaps extended to landing flap position. And what's that? That's right, 30 or 40, and the landing gear is not yet down, because there's no time that you would be at flaps 30 or 40 without having the landing gear extended. Outboard flap asymmetry protection. That's a built-in system that has a follow-up device so that if there's ever a difference in your left and right outboard flaps, all the flaps will stop moving. All the outboard flaps will stop moving, and you will not get a greater asymmetry than what is sensed by your asymmetry protection. And the ground proximity warning system. Remember, it was looking for landing flaps. It was looking for the flaps in the landing position, 30 or 40. When we get how high? Well, somewhere below 500 feet. And it is sampling the flap position only at the outboards. Okay, now let's look at the inboard flaps. What's on that? Well, not nearly as much. The stall warning system gets its inputs from the inboard flaps. Now that's important to know because what if we had, again, a split flap condition where our inboard flaps were extended properly but our outboards were not? Well, in that case, the airplane would think we have all the flaps we need. And we would get a stall warning system, we would get a warning of an impending stall probably at a lower airspeed than the airplane would actually stall at. Likewise, what if we had a split flap condition where our inboard flaps were not extended and our outboard flaps were? The airplane stall warning system would think we didn't have any flaps. So we would get a stick shaker much in advance of the actual airplane stall. So the stall warning system, inboard flaps. Inboard flap asymmetry protection, very similar to the outboard flap asymmetry protection. Works slightly different, but it does the exact same thing, and that is it cuts off hydraulic pressure to the flap actuators, which turns the torque tube, the flap motor, so that the flaps won't move any further and aggravate the asymmetry. Lower rudder load limiter. Remember we said that if the flaps are extended, we have the rudder load limiter taken out of the picture so that we get full pressure to the lower rudder as opposed to reduced pressure to the lower rudder, depending on if the flaps are extended or not. Where does it talk to? It talks to the lower rudder, to the inboard flaps only, to decide whether the lower rudder load limiter is in the high pressure or the low pressure position. Air conditioning pack cooling fans also talk to the inboard flaps, and in parentheses I put auto pack trip. If you have a long-bodied airplane that has the auto pack trip system, it also gets its input from the inboard flaps. And remember, the things that it takes to arm the auto pack trip system, one is flaps not up. Airplane on the ground, all EPRs above 1.5 EPR. Okay? The flaps it's looking at to say flaps not up are the inboard flaps. And the speed brake flap warning horn. That's an intermittent horn which sounds if the speed brake is extended at the same time the flaps are extended. The reason for this is that with the flaps extended, you know, there's a gaping hole left at the trailing edge of the wing. You've got an increased airfoil. When the speed brake is extended, you've got an increased roll authority. And when the speed brake and flaps are extended at the same time, you have a tremendously increased roll authority. It'll be something that makes fighter pilots happy, but it'll also sound the horn because the airplane could very easily go out of control. So what we have is an intermittent warning horn. Getting back to this auto pack trip, and over here the takeoff warning horn, you can see now that if you had an aircraft that had the auto pack trip system, you would always know when you had split flaps on takeoff, wouldn't you? Sure. If your outboard flaps were not down to the takeoff range, you'd get a takeoff warning horn. And if your inboard flaps were not extended, your auto pack trip would not arm. So that would be one other way if you end up pushing up the power and you don't get a takeoff warning horn, but at the same time you don't get a green light telling you your auto pack trip system is armed. Could be you got split flaps. Check your flaps again. Now I told you I'd give you a little memory aid to remember how these things work. For me it's easiest to just think that the short list is the inboards. Everything else that works off of flaps is off the outboards. And for the short list, I think of SILAS, SILAS. Stall warning, inboard flap asymmetry protection, lower rudder load limiter, air conditioning pack fans, and auto pack trip if we have it. Speed brake flap warning horn. SILAS. If I can remember those 5 things, then all I have to do is remember that everything else that's flap operated comes off the outboards. And if you're like me, you probably have a good memory, but it's just a little too short. So that'll probably help. Coming over here to look at the landing gear handle, I would like to discuss one other horn, and that's the landing gear horn. And that comes on any time the throttles are brought near idle, or any throttle is brought near idle, and the gear is not down and locked. What kind of horn is that? Sure, it's a steady horn. And can you silence it? We do it every day with the horn cutout switch on the lower pedestal. So now we've discussed all the horns in the airplane. As a quick review, what are they? Well, we have the landing gear horn when the throttle is brought near idle. It's a steady horn, and it can be silenced by pulling the cutout switch on the pedestal. We've got one other steady horn, that's the landing gear flap horn, and that comes into effect when the landing gear is not down and locked, and the flaps are extended to landing range, flaps 30 or 40. Those are the two steady horns. The two steady horns are both gear horns. Okay? Can we silence that other gear horn? No, we can't. We have to correct the situation. We have to raise the flaps up above 30 or lower the gear to silence that horn. Okay? What are the other horns? The takeoff warning horn. The takeoff warning horn, trim not in the green band, flaps not in the takeoff range, or speed brake not stowed. Okay? What kind of horn? Intermittent. Speed brake flap warning horn. Speed brakes and flaps extended at the same time. What kind of horn? Sure, intermittent, because only the landing gear horn is a steady horn. Any other horns? Why, yes, that's absolutely correct. The altitude warning horn when the cabin altitude goes above 10,000 feet. Can we silence that? Yes, we can. We can make the cabin get below 10,000, or we can press the horn cutout on the second officer's panel. Next to the landing gear handle, we've got a series of lights, 6 lights, 3 labeled A and 3 labeled B, ailerons, rudder, and elevator. And what these do is, these annunciator lights tell you of low pressure, low A system pressure to the ailerons or to the rudder or to the elevator, and likewise low system B pressure to the ailerons, rudder, and elevator. So we, from the front of the airplane, we know that we have a hydraulic system failure, as well as from the second officer's panel. When else would these lights come on if we didn't have a hydraulic failure? Why, sure, if we turn off that particular hydraulic power switch on the overhead panel that we discussed before. We mentioned the tail skid before, and let me just digress and talk about that for a minute. On this airplane, the tail skid is not an electrical tail skid, it's hydraulically operated. The tail skid light is on the forward panel. How does that work? Pretty good. It works by when the gear is raised, the tail skid comes up. When the gear is lowered, the tail skid comes down. Works hydraulically. And what hydraulic system would you suspect powers the tail skid? Why, sure, the A system, because that's the same system we use to lower and extend the gear. How about on the other airplanes, the short bodies? Well, on the short bodies, there's a small micro switch right up here at the full up position of the landing gear lever. And when the landing gear lever is placed to full up to hit the micro switch, it tells the tail skid time to come up. And the tail skid motor starts on its way up. And the tail skid will drive until it is fully up, whether or not the landing gear handle is placed down to the off position. When the tail skid is moving and on its way up, the light on the second officer's panel will illuminate. Unless you've already placed the gear handle back to the off position, in which case the light goes out even though the tail skid continues to move. When the gear is extended, when the flaps finally reach position 15, which flaps? Sure, the outboard flaps. Finally reach position 15, then the tail skid will start to extend. And if the flaps are raised at any point, the tail skid will stop extending. At any point prior to full tail skid extension, if the flaps are raised, the tail skid will just stay at whatever point it was at when you raise the flaps back up. Oil low pressure lights, one for engine number 1, engine number 2, engine number 3. They go right along with the oil pressure gauge on the second officer's panel. They're also called oil filter bypass lights, because if this light comes on and your oil pressure is good, it means you got a filter bypass. If the light comes on and the oil pressure is not good, it means you lost oil pressure. Now I know what you folks are thinking. You're thinking, George told me that the oil pressure gauge on the second officer's panel is AC powered, and I'll bet you that during a battery start, since we don't have an oil pressure gauge, we can rely upon that light to go out to tell us that we got adequate oil pressure. That's probably what you're thinking, right? Now that's the way I would have designed the airplane too, but that's not what Boeing did. And in fact, these lights don't work on battery power. So you will not have this light going out as an indication of proper oil pressure. You won't have these lights at all until you've AC powered the airplane. So don't think that that's going to work for a battery start. It would have been a great idea, but it doesn't work. Okay, on each side of the instrument panel, as you're well aware, you have a below glide slope amber light. You can push that to silence the glide slope warning function of your GPWS. And here's your GPWS itself, and you can press to test that thing. Over here on the other side of our instrument cluster, we have a couple lights. One is low press, elevator low pressure. What that means is, first of all, the light only comes on when the autopilot elevator channel is engaged. And it means you have low hydraulic pressure to whatever system is powering the autopilot. Remember, we can select System A or System B to power the autopilot. And what it's telling us is we don't have enough pressure. It will not disconnect the autopilot. The light will come on to tell you you don't have enough pressure, and you must disconnect the autopilot. Stab out of trim light. That means the stabilizer and the elevator are not paired with each other. Now, is that any problem? Well, it may and it may not be. You know, when you have the autopilot engaged, and again, this light only works with the autopilot engaged. When you have the autopilot engaged, you're using the low speed or cruise trim motor, aren't you? Sure. And that will be trimming the stabilizer so that, hopefully, the elevator stays paired with the stabilizer. Well, what would happen if maybe we were doing 350 knots and we pull the throttles back to idle and start slowing down? Well, the airplane is going to require greater and greater nose-up trim, and maybe the airplane is slowing down so fast that the cruise trim cannot keep up with the trim requirements. In that case, the autopilot starts holding up elevator. When the elevator is sufficiently unpaired with the stabilizer, that light comes on and says, hey, the elevator is out of trim, or the stabilizer is out of trim. Okay? If you see the autopilot trimming the stabilizer, then no big deal. It means it's trying. Give it time. If the autopilot is not trimming the stabilizer, well, you got a problem, because the autopilot is holding in some elevator that is not called for or not being responded to by the stabilizer. And in that case, when you disconnect the autopilot, what do you think is going to happen? That's right, you're going to have a handful of airplane. So most procedures tell you to go ahead and look at your elevator position indicators, trim the elevator till it is paired with the stabilizer, and then disconnect the autopilot, or then leave the autopilot engaged. In either case, the stab out of trim light should go out. There are two types of yaw damper indicators. One is a yellow flag like we see here that says YD, yaw damper. Now, if you have a yellow flag, that means that your yaw damper is not electrically powered. And of course, we've got two yaw damper switches directly below this instrument. So in this particular case, the lower yaw damper, the lower rudder yaw damper, is powered because we don't have a flag. The upper rudder yaw damper is not powered because we have a flag. Talking about electrically powered. We have one other system, though, and that consists of green power on lights. Power on lights. What if we looked up there and we saw one green power on light and the other power on light is not illuminated? Well, we got a problem. It could be that the green light bulb's burned out, or it could be that we really have lost power to the yaw damper. How are we going to tell? Well, I can tell you one way. Well, obviously, when you're taxiing out, you turn the airplane, you see if the yaw damper moves the rudder the opposite way. Another way, before you even have hydraulic pressure on the airplane to move the rudders, you could turn off the system that you know is working and then try to engage the autopilot. If you can engage the autopilot, because you have to have a yaw damper available to engage the autopilot. If you can engage the autopilot, it means that the yaw damper is working. and it's just a burned out light bulb. If you can't engage the autopilot, it means the yaw damper really isn't working. So that's something you might keep in your bag of tricks, although everybody knows you don't take a bad airplane. Okay, speed brake. You know, on the advanced airplanes, we have automatic speed brake deployment for a rejected takeoff or following landing, if we so elect. If we want to get automatic speed brake deployment following landing, we arm the speed brake. We do that by placing it in the first notch. We'll get a green speed brake armed light on the forward panel, and that means that once we touch down, bring the throttles to idle, the speed brakes will extend. If we get an amber speed brake do not arm light, it's telling us, hey, do not arm the speed brakes. Something is wrong. It has done a self-test of its circuitry, and things do not look good. So in that case, we're going to have to manually deploy the speed brakes, just as we do in all non-advanced airplanes. Well, do we need to arm it before takeoff? What if we're going to reject the takeoff? Wouldn't it be nice to have automatic speed brake deployment? Do we go ahead and arm the speed brake? No, we don't. What would happen if we did arm the speed brakes? Well, you'd get a takeoff warning horn, because remember, one of the things was speed brake lever down. So that's not going to work. How do we get automatic speed brakes? I'll tell you. All you need is a main gear spin-up signal that equals 60 knots. That arms this thing so that if you ever place the throttles in reverse, like you would on a rejected takeoff, the speed brake lever will automatically come all the way back. Now, what throttle it is unimportant, because it's a couple throttles, and the takeoff warning horn on the advanced airplane works that way too. It works off throttle actual EPR rather than throttle position, and the throttles have different things on them as far as reversing the micro switches, but knowing which throttles it is, I don't feel is important. Okay, down here are the start levers, which we discussed before. The cruise trim switch, and we've discussed that. What kind of trim is that? Sure, slow speed trim. A stabilizer trim light, which illuminates whenever we use the trim, either cruise or high-speed trim, unless the autopilot is engaged, at which time this light is deactivated. Two stabilizer trim cutout switches, one to cut out the high-speed main electric trim, and the other to cut out the autopilot and cruise trim. And that should complete our discussion of the forward panel. Things such as avionics and instruments that you use every day don't really bear relevance to our discussion, because we are making this for several different airlines who have different types of avionics gear. Plus, you use this stuff every day. So now, why don't we go through a practice oral, where I'll just ask typical oral type proficiency check questions, and we'll discuss the answers to them, okay? And the first oral question I'm going to discuss is one that we just discussed 5 minutes ago, and that is, what are the typical warning horns that you'll hear in the 727 airplane? And part two, are they steady or intermittent? Okay. Let's talk about the steady horns first. Which are they? Good. Gear-related horns are steady horns. So what does that mean? That means the landing gear is not down and you pull any throttle near idle, or it means the landing gear is not down and you place the flaps to the 30 or 40 position. The first case, where you had the throttle near idle, would be capable of silencing that with the landing gear horn cutout switch on the lower pedestal. The second case, we have to either extend the gear or retract the flaps. Okay, what are some other horns? Okay, we have the takeoff warning horn. Once again, trim not in the green band, flaps not in position in a takeoff flap range, which is 5, 15, 20 or 25, 20 only on the advanced airplane, and speed brakes not completely down. Okay, what other horn? The altitude warning horn on the second officer's panel, capable of being cut out with the cutout button or by lowering the cabin altitude again below 10,000 feet. And the speed brake flap warning horn, which you will get when you have the speed brakes and the flaps extended at the same time. I would say, by the way, that that knowing the location of the horn circuit breaker would be an important thing. Why? Because there are some immediate action emergency procedures that require you to pull that thing. Ditching would be one such case where we have the flaps extended to a landing position with the gear up. Now, it's going to be hectic enough when we're ditching an airplane without having a horn beeping at us too. That's a horn sounding at us, not beeping. Okay. By the way, just to digress for a second and talk about the circuit breaker panels, I know most of you are familiar with it. Remember, the circuit breakers on the 727 are arranged by system when they are near the second officer's panel. That is to say, they are labeled P6, 1, 2, 3, and so forth, and they are basically arranged by aircraft system rather than power source, except for the ones at the very bottom, which are called P6, 11, 12, and 13, where they are arranged by power source. P6, 11 is bus number 1, P6, 12 is bus number 2, and P6, 13 is bus number 3, and all of those arranged by power source are high current items, high load items. Now there are some control circuit breakers for those same devices which are arranged by system on the second officer's upper circuit breaker panels, P6, 1, 2, and 3. Such as what? Such as the air conditioning pack cooling fans. The fans themselves are high load items. So they're on P6, 11, 12, 13, that area. The fan control is not a high load circuit breaker. That just tells the fan when to turn on and off, and so that is arranged by aircraft system under air conditioning and pressurization. Okay, on with our questions. Which instruments on the center instrument panel are self-powered? Okay, N1, N2, and EGT. What happens when you pull one of these engine fire handles? All right, we stop the flow of all fluids through the engine firewall. We stop the flow of all air bleeds through the engine firewall. We arm the appropriate engine. We route the bottle pressure to the appropriate engine. We arm the fire discharge bottle button. We trip the engine field breaker, the generator field breaker, after a short delay, like 10 to 15 seconds. And if it's engine number 1 or engine number 2, we disarm the hydraulic low pressure light. What does it mean when you get one of these bottle lights on, fire bottle lights? It means low pressure. It does not mean anything else other than low pressure. On to the overhead panel. What does the presence of the stall warning off light indicate? It indicates that you've either lost power to the stall warning computer or you have lost heat to the vane. Period. What will set off the GPWS? Several things. Being below 2,450 feet above ground level and having an excessive rate of barometric descent. Being below 1,800 feet above ground level and have an excessive closure with the terrain. Being below 500 feet above ground level and not being in the landing configuration, which is landing gear down and flaps at 30 or 40. On takeoff or missed approach and descending prior to reaching 700 feet AGL. Or being below 1,000 feet and 1 1/3 dots below glide slope with the landing gear extended and the number 1 navigation receiver tuned to an ILS frequency. Those are the things that will cause the GPWS to sound. What position of this switch will cause this emergency exit lights unarmed light to illuminate? Well, the emergency exit lights unarmed light will come on if the emergency exit lights are in the off position, because then they're not armed, or if the switch is placed to the on position, the lights will come on. At what position of this switch are the self-contained emergency exit light batteries being charged? The self-contained emergency exit light batteries are being charged when the switch is in the off and when the switch is in the armed position. And of course, when the switch is in the on position, or if it's in the armed position and they have tripped on, the batteries are not being charged. They're being discharged because the lights are being used. How do you erase the cockpit voice recorder? Well, you must be on the ground as sensed by the left main gear strut switch. You have to have the parking brake set, and then you have to press and hold the erase button for 7 seconds. What will happen if you take off with the flight recorder switch in the off position? Well, it will turn itself on when you lift off. Is that adequate for FARs? No, because the thing has to be operated from the beginning of the takeoff roll. But it will cover you at least while you're in the air. What happens when you position the alternate flaps master switch to on? 4 things. Hydraulic control to the trailing edge flaps is lost. Hydraulic pressure to the leading edge devices is cut off. These 2 inboard and outboard electric switches are armed. And the standby pump is turned on. What kind of ignition do you get in flight, high or low energy? That's a trick question. You get whatever kind of energy is called for by your start lever. You get high energy if it's placed to start. You get low energy if it's placed to idle. Good job. You fielded that very well. Let's go to the second officer's panel and talk about that, ask some questions about that. When you disconnect a CSD, can you reconnect it in flight? Now, that was a freebie. No, you can't. It can only be reconnected on the ground. If you turn off, if you open the number 1 generator switch, can you still get essential power from generator number 1? Yes, you can, because as you recall from a couple hours ago, essential power comes right from that little screw there, the essential screw. So even though the generator switch is open, the generator is not providing power to the bus, you can still get essential power from it. What are the limits if you're on 2 generator operation? The limits are 54 kilowatts. What are the limits if you're on 1 generator operation? Then the limit is 36. Does that make sense? You see, 54 happens to be 1.5 times 36, and if you're on 2 generator operation, we want to limit you to 1.5 times the max 1 generator load, just in case we lose 1 more generator. Because that 1 remaining generator should be able, for a very short time, to handle 150% of its rated 36 kilowatt load. What's the limit for all 3 generators operating? 102.5. Okay, here's a question for you now. We're down to 2 generator operation, and we have turned off everything that we can to download the airplane, and we're getting 60 kWs of total load. 60 kilowatts. We're down to generators number 1 and number 2. Generator number 3 is dead. And our total load is, let's say, 30 and 30, which is 60, and that exceeds our limits. What are we going to do? And we have turned off all the unessential electrical equipment we can. We'd like to turn off the galley power, but there's a girl on a dialysis machine that's plugged into the galley, so we can't do that. What are we going to do? What we could do is, rather than running parallel, we could run isolated. We could let generator number 1 power the number 1 bus and essential power, and we could open the number 1 bus tiebreaker. Now, generator number 1 is carrying 2 buses, essential AC bus and bus number 1, and it's pulling, say, 30 kW. It's allowed to pull up to 36, so we're okay there. And generator number 2 is powering its own bus, plus through the bus tie, it's powering bus number 3. And it's pulling 30 kW, and it's allowed to do that because its limit is 36. So we're okay. The girl that's on the dialysis machine doesn't have to die after all. And the nun can continue to sing to her. Okay? We're taxiing in, and we want to place the essential power selector to APU. What do we need to do? What set of conditions must be satisfied first? Well, we have to have the APU running, and the APU field breaker must be closed. And then we can select APU with our essential power switch. What's powering essential power at this point? Very good. Whatever's powering the tie bus is powering essential power. Whatever's powering bus number 3 is powering essential power, because we're getting essential power off of bus number 3, which in turn is probably being powered by whatever's powering the tie bus. How much of an imbalance can we have between fuel tanks number 1 and number 3? Right, 1,000 pounds between tank 1 and 3, lateral imbalance. How about between tank number 2 and either number 1 or number 3? Well, number 2 tank can go down to 2,000 pounds below either tank 1 or tank number 3, whichever causes that 2,000 pound imbalance. Let's say that we're down to 10,000 pounds of fuel in tank 1, tank 2, and tank 3. We're down to essential AC power. How much fuel can we dump? Well, if we're down to essential AC power, the only boost pumps that are working are what we call Seattle and Miami in tank number 2. That's the left forward and the right aft boost pump. So we can only dump out of tank number 2. Now, we could theoretically dump down until we reached our undumpable limit, which would be 3,500 pounds in tank number 2. However, we would be exceeding our imbalance limit, which is a center of gravity limit, by the way. We don't want tank number 2 to get any lower than 2,000 below tank 1 or 3. So in this case, all we could dump would be 2,000 pounds. We could dump down until we got 8,000 in tank number 2, and that's it. What are the limits for fuel tank temperature? Well, the fuel tank could go down to minus 36 degrees, and it could go up to plus 49 degrees. What would we do if we had a fuel icing light? Well, if you have a fuel icing light, and this will be an airline-specific procedure, if you have a fuel icing light, you turn on all 3 start switches to flight. You ensure that you have positive boost pump pressure to all 3 engines, and then you position all 3 fuel heat switches to on. What indication should we see when we turn the fuel heat switches on? You should see a slight drop on the engine pressure ratio if the throttles are up far enough to see that. That is, not at idle. You should see the oil temperature start to rise, because the oil, as you remember, is not being as efficiently cooled now that we have bleed air heating up the fuel that cools the oil. The ground interconnect valve. Under what condition is the ground interconnect valve an active valve switch, an active switch? When is that switch enabled? That switch is only enabled when external power is plugged into the airplane or the airplane is being powered by the APU. Are there any other conditions that sound the same way? Is there any other device on the airplane that works off the same 2 sets of interlocks? Yes, that's right. The stall warning power off lights work the exact same way, don't they? Those power off lights will illuminate whenever external power is placed on the airplane, is plugged into the airplane, or whenever the APU is powering the airplane. So you could say that these 2 stall warning power off lights, or 1 if you only have 1 on your airplane, the stall warning power off light tells you when that ground interconnect switch is an active switch. And you can go out to the airplane, and if you're on airplane power with external power disconnected, you can throw that switch all day and you will not get system beat pressure over to the A side. Won't happen. Would it be a good idea to use the interconnect valve if you've had a system A failure and now you need to taxi into the parking ramp? No, I would not say it's a good idea. First of all, the B system pumps are of a much lower capacity than the A pumps. Second of all, You're using your B system pumps for braking also, and you might just overload those pumps trying to use it for steering and braking at the same time. And third, perhaps most important, to get that valve to work, to get that switch to be an active switch, you must have the APU powering the airplane. And if the APU is powering the airplane when you're taxiing, if it flames out, you've just had a total electrical failure, which means you've lost your B brakes because they're electric pumps. So overall, I would say it's not a very good idea. Where is the A system hydraulic fluid cooled? The A system hydraulic fluid is cooled in fuel tank number 3. Where is the B system hydraulic fluid cooled? It's cooled in fuel tank number 1. Where is the standby system hydraulic fluid cooled? Wrong. It's not cooled. Okay. Hydraulic brake interconnect. What's that used for? Well, it's to allow the A system to pressurize the brakes. Will allow A system to do anything else for the B side? No, it won't. Would you anticipate, if you had a brake leak, using the brake interconnect so that if you've lost all your B system fluid through that brake leak, now you can open it up and use the A system to pressurize the brakes? Well, I would say that that depends. If you had to get the airplane stopped, if your pneumatic brakes were shot also for some reason, you might consider it, but be aware that the whole time you're doing that, you're losing A system fluid also. If you had to get the airplane stopped and there was no other way, then you'd probably consider it. But in general, it's not a good idea because you're going to end up losing all your A system fluid out that same brake leak, which means you'll lose your nose gear steering, among other things. What would be your indication of a failed TR? Your indication of a failed TR would be no current when you select that TR. The voltage would still be good. What does it mean if the center light lights up? That's a lower aft body overheat light. It means you've got a bleed air failure, a bleed air leak somewhere, and it could be one of many places, including the aft air stairs, the keel beam, the cargo pit area. What does this amber light, passenger oxygen amber light, mean? It means that the passenger oxygen manifold is pressurized. What are the ways of pressurizing the passenger oxygen manifold? Well, there are several. You could have an automatic pressurization by cabin altitude going above 14,000 feet. You could have a manual pressurization where you pull the manual handle, which is normally, on most airplanes, below the carpet in the center aisle, just aft of the cockpit door. You could electrically pressurize it by taking this switch and going from normal to on. How many oxygen bottles are there in the airplane? There are 3, 1 for the crew and 2 for the passengers. What would the indications be if you were making a pack-off takeoff with the auto pack trip armed if you lost an engine? Well, your indications would be a green light because the auto pack trip arming light would have come on, arming the system. We said it was armed. The green light will stay on. You'll get 2 pack trip-off lights illuminated even though the packs are left off. You see, the auto pack trip system doesn't know if you turned the packs on or off. It just makes sure that they're off when the system trips. So your indications would be, even though the packs were off, your indications would be a green light which remains on and 2 amber trip-off lights for the packs which would remain on also. What's the proper way if the packs had been on and the auto pack trip system tripped? What's the proper way to reset it? There's only one proper way, and that's to use the flight handbook, which tells you, because there are three sequences of steps that you could take here, and 2 of them are wrong. So the thing to do, of course, is turn the packs off, reset the system, and then go to cutout. But any other order of that will not be correct, and it would end up with your pack fans turning on suddenly and putting a very large drain upon the 2 remaining or 1 remaining generators that you have. So it's not a good idea to do it by memory. Instead, you take out the book and you look it up. Where do you want to have the pack temperature gauge? Where do you want that to read normally during flight, during cruise? Well, if it's a short-bodied airplane, you want the pack temperature to be right in the green band, right at 100 degrees. These are centigrade scales. How about for the long-bodied airplanes? Well, then you want them to read between 30 and 40 degrees. What if I look up just as the left pack trip-off light illuminates, and I notice that my left pack temperature gauge is up around the 10 o'clock position, slightly above normal, but not anywhere near the red band? What caused that pack to trip? Well, it wasn't at the red band, so it was not compressor outlet temperature, was it? Because we read compressor outlet temperature at this temperature gauge. So it must have been turbine inlet temperature being excessive, and that's not something we can read anywhere. But that is one of the conditions that will cause a pack to trip. What is the other condition that will cause a pack to trip? Excessive duct temperature. What would have happened prior to that? We would have gotten a duct overheat light. At what temperature? 190 degrees duct temperature. What would have come into play prior to that if we were in the automatic range? The topping circuit would have come into play at 140 degrees duct temperature. What would that do? That would stop. What will cause the off-schedule descent light to illuminate? Well, starting any descent prior to reaching our planned flight altitude is dialed in the flight altitude window of the electronic controller. If we go to manual AC and we move the outflow valve switch to close, and the flight ground switch is in ground, what kind of movement will we get? Continuous. How about if it's in flight? Incremental. Does it matter if we're on the ground or in the air in this case? No, it doesn't. Well, those are the samples of types of questions you could expect on a proficiency check oral. I'm sure you can think of many others. I'm reminded whenever I think of airline pilots of the suave and debonair 727 pilot that went into the bar, saw a lovely young thing down at the other end of the bar, said to the bartender, "Barkeep, buy that girl a drink, put it on my tab." It must have been 2-for-1 drinks or something like that, knowing how cheap airline pilots are. But the bartender says, "Save your money, buddy, she's a lesbian." He said, "Listen, you buy her a drink and put it on my tab. I'm buying." So the bartender set her up with a drink. She drinks the drink. The pilot says, "Hey, barkeep, set her up with another drink, put it on my bill." The bartender says, "I told you she's a lesbian." He says, "Listen, you give her a drink and put it on my bill." Bartender gives her a drink. Pilot takes his drink, swaggers over to her. "So tell me, how's everything in Beirut?" Well, folks, this completes our briefing. And just remember, there are three qualities you have to make a really great airline pilot. One, you have to have good coordination, because you're doing a lot of motor skills all the time. Your job depends on it. Two, you have to have a good memory, because there are going to be times when emergencies and problems arise and you can't always take out the checklist. You have to just, off the top of your head, know what to do. You have to have a good memory. And the third is, darn if I can remember. See you.